Alright, welcome back. This is Thermodynamics II. Let's go to School of Mines and Technology. We're on homework 4, which is fugacities. And the second problem asks, what is natural log of phi I hat equal to 1 hat? 1 hat. Oh, is it I hat or could be I? Nope, it's saying specifically component 1. Okay, so for component 1, what's it equal to? And so, well, I have a phi, so that's probably a fugacity problem. Probably. Okay. Is it pure or mixed? Well, I see terms that say mix. That's a good hint. But that doesn't always mean it is a mixture problem. I can have mixture stuff and it be a pure problem if I'm asking about Lewis fugacity. Okay. Now, it does not say anything about the Lewis fugacity rule, okay? The other thing it's asking for is phi 1 hat. And what does that hat mean? That's right, we're having a party. It's a mixture. Okay, so we're definitely a mixture thing, okay? And so, by default, I have to do equation of state. Well, I have an equation of state, okay? My next thing is to decide, okay, what equation should I use? Well, when I'm doing this, what I always want to do is I want to put it in terms of z. Okay, so when I put it in terms of z, things aren't going to exactly work out. Okay, so I want to put it in terms of z. Let's do that. Alright, z is equal to pv over rt. Okay, and so we have So we want to multiply p over rt on that thing. Okay, so z is equal to p over rt times a mix times t squared over p cubed. Okay, so that goes to a squared, goes away, that goes away, that goes away. Okay, and so z is equal to a t over rp. Okay. Alright. AP squared. AP squared. RP squared. Okay. So z equals AT over RP squared. Okay. Now I need to decide, okay, I know I'm equation of state, but which equation do I use? I have those two equations. I don't have my cheat sheet with me, so I'm just going to have to guess. I'm not going to write down the actual questions. I'm going to just write down the approximate equations. Okay, but you will have your cheat sheet. Okay, I just don't remember them off the top of my head. So natural log of phi I is equal to either 0 to p of partial molar z I minus 1 dp over p, or natural log of phi I hat is equal to, there's some stuff in front, I can't remember exactly what, minus infinity to v of partial molar zi minus 1. Oh wait, not partial molar zi. This one's different. This one is, there's stuff, and then there was minus infinity to v, and there was d and z, d and I, t, v, and j not equal to I minus 1, dv over v. And you might be like, well, Dr. Hadley, isn't that a partial molar z? No, because it is not a constant pressure. Okay, it's a constant volume, so that doesn't count. So this is the notation we're going to see, of course, the rest of the equation, but again, I don't remember it. Okay. Key here, though, is like, okay, I choose my right equation. Okay, that's an important step in understanding how things work, especially the math. Okay, well, how do I decide which one to choose? Well, what letter do you see? Or rather, don't see. I see a P, I don't see a V. So, I don't see a V, I see a P. Okay, so that's the one I want to do, okay? Okay, well, I need to... So now that I've chosen which equation, now I just need to kind of use it. Now, with the mixtures, I have that added step of doing this derivative first. Well, that derivative, of course, is just a partial molar z, but I need to do it. Okay, and so let's do that really quick. And so now it becomes a partial molar property problem. Okay. So partial molar z1 is equal to d nz dn1, a constant t, p, and j not equal to 1. Okay. Now, I have to ask, can I do this as binary? No, there's n components. It doesn't tell you how many components it says. There's n components. Okay. So I definitely have to use that one. Okay. So I use that one, and, well, I multiply by n. Okay, so I'm going to multiply by n. Okay. And really, but t, p, and r are all constant. So I'm really just kind of finding what's the partial molar A. Okay. So in reality, this will equal partial molar A1 t over rp squared. And there are some homeworks where that's all I'll have you do. You know, I won't ask you to do the math on partial molar AI because you've done partial molar properties before. Okay. Now in this case, I'm going to have you because it's really simple. But, you know, I might be just, okay, leave, you know, partial molar constants, because that's essentially what it is. It's a partial molar constant, as is that notation. Okay, so, all right. But let's just do that really quick. So, again, multiply that by, you know, so, NA mix is equal to summation of, because, okay, so this is summation of ni over n total ai. Well, they're all divided by n total, so they all have a common denominator. So if I multiply by n total, I should get summation of ni ai. Okay, that's not too crazy. All right, but how do I take that derivative? I have a summation. My head's going to explode. Well, in these cases, what I like to do is I like to do a pattern. Okay, like I like to do a representative example, so like a 3-component system, to see, well, what pattern do I see? Okay. So let's just say it is, you know, n1a1 plus n2a2 plus n3a3 plus some stuff that I'll figure out later once I do my pattern. Okay? I take the derivative of that with respect to n1, keeping t, p, and nj not equal to 1 constant. Okay, so partial molar a1. Okay, and what's the derivative of this with respect to n1? Yeah, it's a1. Okay. What's the derivative with respect to n1 for n2? Well, is n2 constant? Yeah, it's constant. So that's 0. Okay. What about with respect to n3? That's also 0. And what do you think would be for n4? So it is, you know, partial molar a1 is just a1 in this case. It's actually really simple. You know, don't let those summations scare you. You know, again, there's always a pattern to them. So you just have to be able to recognize the pattern. Alright, so I recognize the pattern. I've done my derivative. I've done my partial molar property thing. Okay, now what do I do? Well, now I just plug into the original equation. Okay, and so natural log of phi 1 hat is equal to 0 to p. Partial molar z, well, let's plug that one in actually. So partial molar a1 t over rp squared minus 1 dp over p. And then I just want to distribute, you know, that over p and then do my integral. Okay, so let's distribute it first. Okay, so 0 p, I have partial mod A1t over RP cubed minus 1 over P dP. Okay, and then I just do my integral. Let's do that up here. Now I just integrate. Okay, so natural log of phi v1 hat is equal to partial molar A1t, because that's constant, over RP squared minus 2. Okay. Minus the natural log of P from 0 to P. Okay? Now, this is why it's infinitely important that you show all of your work. Okay? And not just, because I know half of you are just going to be like, oh, well then it's just this minus natural log of P and my answer's done. No, show your work and you'll find out it's not done. I have minus 2 partial molar A1 T over minus, I don't know why that's a minus, over RP squared minus natural log of P plus 2 partial molar A1, oh that's not minus, that's a partial A1 T over R times 0 squared plus natural log of 0. Tricky. Alright, so it's tricky. Okay, it's one of two things. Okay, so what is 2 divided by 0? It's infinity. Okay. Well, what's the natural log of 0? Now that's the one that's tricky, because it depends upon where I approach. Now, can I have a negative pressure? No, I can't have a negative pressure, so I'm going to be approaching from the positive. Okay? And so negative, so natural log of 0, okay, that's going to give me an error. But if I put a natural log of, 10 to the minus 10, well, this approaches minus infinity. And what's any number subtracted by itself? Yeah, they cancel each other out. So, okay, if you put the answer, you'd get it right, but not always. Okay, and so you have to watch out. It's in this case you do, but not always. And so in this case, though, in the end, you do get minus 2 partial molar A1t over RP squared minus natural log of P. And there's your natural log of P. But, plug it in, because I've had situations where this was really like infinity plus infinity. And so it was just infinity at the end.